Okay, everyone, so let's take a look at today's thinking. We have what is a set? What are the set of numbers? So, a set is a collection of numbers or objects. Each object is called an element or a member of the set. Defining the set of numbers. So let's take a look at the natural numbers. The mathematical symbol for the naturals is two lines that looks like an N. So the definition of this is the set of numbers starting with zero all the way to positive infinity. Now, super important, normally when we learn our numbers, we start with the natural numbers being the numbers that we can count, also known as counting numbers. And then we introduce the whole numbers. The whole numbers are the number zero and so forth. But when it comes to IB includes the number zero when it comes to the natural numbers. Then we have the integers. The integers mathematical symbol is a Z with a extra line. As we know, the integers start off with the natural numbers, but we include both positive and negative. So every single number has a positive and a negative value. Then we have the positive integers. The positive integers are the set of integers, but we're going to denote that we are only talking about the positives. So this set of numbers start with positive 1, 2, 3, and so forth. So the reason that the natural numbers include the number zero is because in IB, we tend to talk about the positive integers. Let's keep going. We have the rational numbers. The rational numbers mathematical symbol is a Q, and the rational numbers include all numbers that can be written as a fraction, where the numerator and denominator are elements of the integers. And last, we have the set of reals. The set of reals are all numbers on the number line. That is positive numbers, negative numbers, zero, fractions, irrational numbers, and so forth. The reals are written as a double R. All right, let's keep going. Our second thinking for today. What is the difference between interval notation and set notation? So we have two notations that we are going to be working with when it comes to IB. We have interval notation. Interval notation is written with parentheses or brackets. Whenever you are dealing with a parenthesis, that means that the number is not included. And whenever you are dealing with a bracket, that just means that the number is included. We have set builder notation. When it comes to set builder notation, we start off with curly brace, X, this line that represents such that. We always include the number that we are dealing with. X is a member of the set of reals. X is an element of the rational numbers. And then we write our values in terms of inequality. So a less than symbol, that just means that the number is not included. A less than or greater than or equal to value means that the number is included. All right, let's do a quick check right here, a quick example using set builder notation and interval notation. Represent each of the following using these two notations. We want set builder and we want interval. Identify each as either an infinite or finite set. So for this first one here, we have the set of all integers between negative 100 and 100. So super important, we have a specific set we want to include. So I'm going to start off with set notation, and to distinguish that, I'm just going to write SN. We're going to say curly brace. We'll say X such that, and we are going to include the set of integers here. So X is an element of the set of integers, comma, where the numbers are starting at negative 100 and going all the way to 100. Since we are dealing with these numbers are only in between, that negative 100 and 100 are not included. For interval notation, IN for short, the numbers negative 100, comma, to 100 are both not included, so we are using parentheses in both ends. Now, the last thing that we want to identify is whether we have an infinite or finite set. Well, here we have, just specifically looking at the inequality or interval notation, we have some start and some finish. So this is a finite set. Number two, we have the set of all reals greater than 1000. So using set notation, we're going to say curly brace X such that X is an element of the reals, comma. Here we're dealing with the number is greater than 1000. So how can we represent that? X is greater than 1000. Using interval notation, we're starting with 1000, that is the smallest value, and we are not including that value. And we're going all the way to positive infinity, and infinities are never included because we don't know what specific number that is. So that also will include a parenthesis. Now here, is this an infinite set or finite set? Since we're heading towards infinity, then this would be considered an infinite set. All right, let's keep going. Let's take a look at our thinking. How can we represent a value that is not exact? So there are two ways. Rounding. Numerical answers may not always be exact, and we will need to round. There are two ways to round numbers: to a specific number of decimal place, DP for short. We can also round up before the decimal place, so to the nearest integer. Now, super important, we round up when the value to the right of what we want to round is 5 or higher. All right, significant figures is another way to represent your values that are not exact. Significant figures tell us how precise a number is. How to determine significant figures? SF for short. All non-zero digits are significant. So those are just whole numbers. All zeros between non-zero digits are significant. Leading zeros in a decimal are not significant, and we have trailing zeros are not significant unless followed by or to the right of a decimal point, and this case is sometimes ambiguous. And as we look further with significant figures, we will refer back to this specific case. So let's take a look at our next example, rounding and significant figures. We have been given a number, 5,153.4497. We want to do some sort of roundings or some sort of representing our number to significant figures. For number one, we want to round to 1 dp, 1 decimal place. So I'm going to highlight one decimal place, and I am going to look to the right. And if that number is greater than or equal to 5, then the highlighted value is going to go up by 1. In this case, the number to the right of the highlighted 4 is a 4, which is less than 5, which means that the number is going to stay as a 4. So our number is 5,153.4. For number 2, we want 2 dp. So I am highlighting the second place, decimal place. What I am going to do is I'm going to look to the right of that highlighted decimal place. And in this case, the number is greater than or equal to 5, which means that that 4 is going to become a 5. So we have the number 5,153.45. Number 3, round to 3 dp. So I'm going to highlight the third decimal place. I am going to look to the right, and that number is a number that is greater than or equal to 5, which means that the 9 is going to go up. So for this specific case, I'm going to be looking at 49. What I'm thinking is 49 is going to go up by 1, which means that the number is going to be 5,153.450. This next one, we have round to the nearest integer. So the nearest integer is the ones place. I am looking to 3, looking over to the 4. 4 is a number that is less than 5, which means that to the nearest integer, this would be 5,153. Number 5 wants us to represent our answer to one significant figure. So I'm going to identify the first number, that is one significant figure. I am going to use my rounding skills. I'm going to look over to the right, and that number 1 is a number that is less than 5, which means that the highlighted number is going to stay at 5. But this time we only want one significant figure, but the number is not 5, it's in the 5,000 range. So I am going to add zeros. This is where that number 4 trailing zeros situation is coming into play. Trailing zeros are non-significant. In this case, those zeros, yes, they're there, but that does not mean that this number represents 4 significant figures. It represents one significant figure. And the last one here, we have round or represent to 2 sig figures. So I'm going to identify my 2 numbers, 2 significant figures. I am going to look over to the 5. Now that 5 is equal to 5, right? Greater than or equal to 5, which means that that 1 is going to go up by 1. So this number would be 5,200 to 2 significant figures. So when we're talking about significant figures, we are incorporating rounding within. And our last piece here, we are looking at scientific form. So thinking, how do we write numbers in scientific form? Any number can be written in the scientific form. That is A times 10 to the k power, in which A is a number that is in between 1 and 10, including 1, but not including 10. We simply move the decimal point after the first non-zero digit. If we move the decimal point to the left, the value of k would be considered positive. If we move the decimal point to the right, that means that the value of k will be negative, will be very small. So let's apply scientific notation here. We have been given x to be 3 times 10 to the 7th power, and we have been given y to be 4 times 10 to the 5th power. Number 1 wants us to find the addition of x and y. So using these scientific form to evaluate. So let me just write what x is, and we are adding these two things, and I'm going to include my y. Now, whenever we are adding anything, right, we always want like terms. Now here, our terms would be that 10 to the exponent. But as I can see, these are not like terms. So what we are going to need to do is we're going to have to make them like terms. Now, to make them be like terms, what I am going to do is I'm going to increase this 5 by 2. So I'm going to add 2 to this. That is going to give me 10 to the 7th power, which is identical to what I have here. So let me rewrite that x piece, which is 3 times 10 to the 7th power. We are still adding these things together, but this time the original number of 4, which my decimal point is right behind, since I am increasing my number or my exponent by 2, I am going to need to move this decimal point to the left 2. Why? Because I am not changing the number. I'm just making it look slightly different. So 4 times 10 to the 5th power is equivalent to 0.04 times 10 to the 7th power. Now that I have 10 to the 7th power, both like, I am going to keep it. And what we are going to do is add my numbers in front. So I'm adding 3 with 0.04, which would just be 3.04. Now, if you do not want to do this, you do not have to do it. You can always expand and add and then just rewrite it back to scientific notation. A little more work, but also doable. All right, let's try number 2. Number 2 wants us to do a product of x and y. So let's just write what x is again. And this time we are multiplying by y. What we're going to do is we're going to multiply the coefficients, which would be 3 times 4, which would give us a 12. And using the laws of exponent, that tells us when we have a common base, in this case base 10, we are going to need to add those exponents. So 7 plus 5 will give me an exponent of 12. But wait a second, this is not written in scientific form, because in order for it to be in scientific form, the value of A must be in between 1 and 10. Again, including 1, but not including 10. And this number is greater than 10. So what we're going to need to do is move a decimal place. So right now my decimal place is in the back, and I am going to move it over right in the middle. That way I have a number that is between 1 and 10. Again, including 1, not including 10. But when I do this move to the left, I need to increase this exponent by 1. So my answer would be 1.2 times 10 to the 13th power. And that is all for today's recap on some basics that we need to know. So keep learning, keep growing, and I will see you in our next video.